Temperature can also vary with altitude. That is, as we move up through the atmosphere, there is also a steady decrease of temperature with increasing elevation in the atmosphere. This decrease of temperature with is known as vertical temperature gradient. Generally, the vertical temperature gradients are controlled partly by the energy transfers and partly by the vertical motion of the air. Now, the observed rate of vertical decrease in temperature is called the lapse rate, and the rate is generally 6.5 degrees centigrade per kilometer. Now, lapse rate indicates the temperature conditions that are found in a stationary column of air that is somehow disturbed. That means some certain special conditions appeared in the atmosphere due to which the general lowering of temperature found in the atmosphere with increasing altitude, that is reversed. This is known as temperature inversion. Now, temperature inversion can be of three types. The first one is known as surface inversion, second is upper air inversion, and the third one is frontal inversion. In surface inversion, as from the name you can have an idea that it is mainly restricted close to the surface area, that means close to the earth surface. And also this type of inversion, this type of increase in temperature with altitude close to the surface lasts for short duration. Now, surface inversion can be again of two types. One is radiation inversion, another is advection inversion. In radiation inversion, this type of surface inversion basically produced by radiational cooling. That means when the Earth's surface radiated the long wave infrared into the atmosphere as terrestrial radiation, the Earth's surface gradually becomes cool, and so does the atmosphere in contact with the land surface. Now, as ground is cooled more rapidly than the air, so the atmosphere close to the surfacial condition that during night time cools rapidly. In contrast, the upper air atmosphere that still becomes more warm compared to the surfacial air. So if you compare the temperature profile of daytime and nighttime, during daytime we can see that the surface was hot due to receiving the insolation, and gradually as we move up through the atmosphere, temperature gradually decreases. But during night time, as the tendency of the surface, earth surface, to radiate the heat, to radiate the energy from its surface in a much faster way compared to the atmospheric gas molecules. That is why the air or the atmosphere close to the Earth's surface becomes readily cool with the emitting of energy from the Earth's surface. So what we found, that during night time the atmosphere close to the Earth's surface is quickly becomes cool, whereas the upper air atmosphere is still warmer. So we get a reverse temperature profile as we move up through the atmosphere. Now this kind of condition will be more favorable, or this type of condition we get more when the uh, time span of night will be more. So when there is a prolonged night time, during that this type of uh, temperature inversion is more commonly found. That means this type of temperature inversion is more commonly found during winter times, when the uh, night time is relatively more. And this type of temperature inversion is also associated with calm dry winds. That means the difference in temperature should be sustained. If the wind is blowing and there is lot of uh, water vapor, then that will hold a lot of uh, temperature. Water vapor basically traps the temperature, outgoing terrestrial radiation. And if wind was continuously blowing, then there is a turbulence, and the entire atmosphere, the gas molecules will mix up. So we did not find this type of temperature profile. So for getting this type of temperature profile, the night time should be long enough, it should be a calm condition, and the wind should be dry wind, not too much water vapor. Now here you can see what happened. This is a normal condition uh, in which temperature gradually decreases up through the atmosphere. And in the right hand picture you can see that the during night time the surfacial temperature becomes cooler, and as we move up through the bed for a short uh, height, we get warmer layer. That means a temperature inversion occurs. Now this warm air basically act as a trap, and it basically shut down all the convection to the more upper layers of the atmosphere. And basically these are mainly restricted within the troposphere, and this warmer layer traps all the circulation, all the dust particles, all the smog to these lower layers. That means they are restricted close to the surface. Now the thing is, if this superficial cooler layer during night time somehow get a lots of water vapor, that means this lots of water molecules in vapor stage are present in this superficial condition, and it is trapped by a warmer air. So this water vapor cannot go past to the upper level of the troposphere. Now when this cooler air comes close to this inversion layer, warmer layer, the water molecules in the cooler air that are slightly cool, they becomes warm when they are in connection in this warmer layer. And that is why a lot of smog or a lot of fog are found over the city during winter time, because this cool uh, water vapor, they become slightly warmer and becomes smog or fog over the city. Mm, Basically, what happens, not only the water vapor, but all the dust particles, all the gases emerging from the factories, emerging from the chimneys, they are trapped into this lower part of the atmosphere. So that creates smog, a um, hazy atmosphere. Now, surface inversion, or this type of surface inversion, particularly the radiation inversion, it is more effectively found in higher latitudes. That is, in those areas where the ground is mainly covered by snow. Now, what happened in the higher latitudes, that the snow covered area, when receives the incoming solar radiation, most of the incoming solar radiation, they are reflected back. Very little amount of energy is taken by the snow covered land surface. So from that amount of energy, the ground surface heats a very little amount. Now at night time, there is unretarded loss of heat by the terrestrial radiation from that snow covered area. So the air near the surface undergoes rapid cooling, and as we move up through the atmosphere, the temperature drop was not so fast. So already in the atmosphere, a snow covered area, the atmosphere is already cooled. Now the land surface receives very less amount of energy from the incoming solar radiation. From that little amount of energy, the atmosphere close to the surface gets a little bit hotter. But during night time, the surface radiates lot of energy from the surface. And as it is a snow covered area, so the atmosphere close to the ground surface gets readily cooler. But the upper air atmosphere, that cannot be readily cooled. So we found a increase in temperature up through the atmosphere. Now the second process of surface inversion is known as advection inversion. In advection inversion, as we know, it basically a density driven flow. Basically the movement of air occurs in a horizontal fashion. Now this type of inversion occurs when warm air passes over a cold surface. Now say for example a watery aqueous condition, a pond or a sea. So during daytime, the sea temperature was gradually cooler compared to the atmospheric temperature in the land's condition. So if this warm air or this warm atmosphere moves towards this aqueous condition, that is moves towards the sea, then due to the cooling, more cooler atmosphere, over the sea, over the ocean, the warm air moves over these cool atmospheric gases. So that means through a small portion of the troposphere above this cooler ocean atmosphere, we get a gradual rise in temperature. So the presence of this warm mass of air above the cool uh, atmosphere over the ocean water body brought some amount of or some kind of inversion, and as this kind of inversion is produced by horizontal flow of air, that is why this type of inversion is known as advection inversion. The second process of inversion is known as upper air inversion. So obviously from the name you may get an idea that uh, in the previous type, that is mainly restricted to the superficial condition close to the earth's surface, and this kind of inversion occurs more higher in the atmosphere. That is why it is named as upper air inversion. Now the upper air inversion is mainly caused by the presence of ozone layer in the stratosphere close to the stratopause. As we move up through the atmosphere, we can see that above the troposphere it lies the stratosphere, and the proportion of ozone gas increasing in the stratosphere, and at the maximum level of stratosphere the concentration of ozone layer is maximum. Now as ozone layer acts as a trap for the incoming ultraviolet rays, so most of the ultraviolet rays are trapped within this ozone layer, and that basically increase the temperature of that ozone layer. Now as we move up through the stratosphere, we get more and more concentration of ozone layer, so the trapping of incoming ultraviolet ray will be more as we move up through the stratosphere. So we found a general increase in temperature up through the stratosphere. Now this kind of increase in temperature up through the um, stratospheric layer from troposphere to stratosphere, and then higher up to the stratospheric layer is known as thermal upper air inversion, and it mainly occurs due to the concentration of ozone layer higher up in the stratosphere. The second way by which upper air inversion occurs is known as mechanical inversion, and it is caused due to subsidence of air and turbulence and convection mechanism. So the mechanical upper air inversion can be of two types. The first one is the subsidence inversion, and the second one is convection or turbulence inversion. Now subsidence inversion, so from the name you can get an idea that this type of inversion is basically produced due to the subsidence of air currents, and this type of inversion is not surface based, that means it's occur in the upper atmosphere, and mainly they are found to develop near the subtropics areas. Now what happened in this process? Due to subsidence of the upper air atmosphere, the thick mass of air now becomes more compact. That means the pressure increase to the lower part of the atmosphere. So more and more atmospheric gases are concentrated in the lower part. So as subsidence occur more and more, pressure within the atmosphere gets increased. Now due to this increase of pressure, adiabatic heating of air is occurred. That means uh, due to the increase in pressure, the gas molecules collide with each other more randomly and thereby producing some amount of energy, and that cause increase in temperature. So by adiabatic heating, that means change in temperature by increasing pressure, and that increasing pressure occurs due to the temperature increase was found in the in this lower portion of the atmosphere. Now, most commonly, it was found that the subsidence of air continues to a particular level within the atmosphere. After that, it diverges horizontally above a lower layer. You can see also in this picture that this subsidence occurs up to a certain level within the troposphere. After that, it diverges horizontally, it splits horizontally. Subsidence inversions are more common in regions of high pressure areas. So obviously when the sinking of atmosphere occurs, the regions becomes a high pressure area. The sinking or the subsiding air compresses and warms the dry adiabatic rate at about 10 degrees centigrade per kilometer. So in these cases, the subsidence continues up to a certain level and occur over the lower layer of cooler air. So you can see from the surface temperature gradually decreasing. Now near the subsiding layer or near this situation, when the divergence occur of this subsiding air, temperature starts rising. So this is known as inversion layer, and close to this inversion layer we found that temperature gradually rising. Now this temperature rising occurs due to the subsidence due by adiabatic heating. So if we look at the uh, temperature profile in this condition, gradually from cooler to gradually in coming to the inversion layer, temperature gradually rising. So again, inversion of normal temperature profile is found, which is occurred due to subsidence of uh, the atmospheric gases. The second upper air inversion process is known as convection inversion. Now, convection currents, or it is also known as turbulence, they set up in the troposphere because of irregular heating of the surface. As we know from our previous classes that sun ray, that is the incoming solar radiation, is not fall in the same amount all the places of the earth. So due to that, irregular heating of the surface occurs. Now due to this irregular heating of the surface, there we found some amount of convection of atmospheric gases. That means movement of atmospheric gases, and thereby the gases mixing vertically up to a certain height. After that certain height, this kind of vertical movement is not occurred. Now in this process of vertical movement of atmospheric gases, the air carried upward is cooled adiabatically, because as we move up through the atmosphere, the gravitational force gradually becomes lower and lower. So the atmospheric gas molecules is now going far away from each other because of the lower amount of gravitational force. So as the atmospheric gas molecules become distant from one another, so there is less chance to collide with each other. So that means the pressure decrease because of the expansion of these gas molecules, because of lowering of gravitational force. And as pressure decrease, so there will be less chance of these gas molecules to collide with each other. So lowering of temperature occurs. That is known as adiabatic cooling, found in the upper atmosphere. Now similarly, in other regions, the air brought downwards, and that is heated at the same by adiabatic rate. So in one place, due to heating, the air goes upward by adiabatic process. It becomes cool in the upper part of the atmosphere. In other way, or in other condition, the air sinks close to the atmosphere, and due to sinking, the pressure increase, so it becomes warm by the same way, that is the adiabatic heating. Now after a prolonged mixing in the atmosphere, the air at the maximum height of this kind of convection motion, that becomes colder than what it was before. So if we took the initial condition, compared to that, the air at the maximum height of this convection flow, that means air in this condition. So if suppose this is the convection shell, and the air in this convection shell portion, that is the maximum height of this convection flow, that becomes colder compared to what it was before, and the bottom of this convection shell will be warmer than what is it was originally before this kind of convection flow. So due to this uh, sinking, pressure increase and it becomes hotter compared to the previous position, and due to the movement in upwards, it becomes cooler compared to its previous condition. Now the transition from this cold upper part of the turbulence zone to the air above this convection shell, which is basically unaffected by this kind of convection flow or this kind of adiabatic cooling or adiabatic heating, there we found a temperature inversion. So where we found the temperature inversion? If this is my convection shell, the temperature in this upper portion of the convection shell, the temperature of the atmosphere gradually becomes cooler as the convection shell proceeds. Cooler gradually becomes cooler with respect to its previous condition. Similarly, the superficial air due to this convection flow, gradually becomes hotter compared to its previous condition. Now, the atmospheric gases above this convection shell, that means these areas, which is not at all affected by this kind of convection flow. Now, if we look at the temperature difference from this layer to this layer, as we move from this to this, we found that this atmospheric gases, this layer of atmospheric gases, that is the topmost portion of the convection shell, the atmospheric gases are cooler, and the above atmospheric gases above the convection shell, those gases are sufficiently warmer compared to these gases. So again we found a temperature inversion, that is increase in temperature up through the atmosphere. Now in certain situations, turbulence in association with heat from the ground leads to the formations of cumulus to cumulonimbus clouds. The third type of temperature inversion is known as frontal inversion. Frontal inversion occurs due to frontal convergence. That means when the different air masses means different with respect to temperature. When the different temperature air masses converge with each other and form a temperature front. Here you can see the cold air and the warm air converge in this portion, and this portion, the junction between the cold air and the warm air, is known as temperature front. This type of inversion is also not surface based. Now when a warm air mass is forced from the ground surface and undercutting of cold air mass occurs, a cold front generates or a cold form formed, because the warmer air being relatively lighter overlies the cold dense air. Alternatively, a similar type of inversion also created when a warm air mass overrides a colder one and forms a warm front. So both type of temperature front, one is warm front and another is cold front, warm air and cold air converge with each other. So what is the difference between the warm front and cold front? In warm front, the warm air that basically moves. So the cold air that is more or less static. The warm air is moving towards the cold air, and as the warm air is less dense, that is less light, so it rides the cold air, that is overlying the cold air. Now when the cold air is more or less static and warm air rides over it, this front is known as warm front. Oppositely, when the warm air is more or less static and cold air moves towards the warm air, then due to the higher density, the cold air undercuts the warm air. The cold air goes below the warm air by pushing the warm air aloft. Then the front is known as cold front. And obviously here you can found along the front the temperature increasing up through the atmosphere. Now, one significant uh, difference of this frontal inversion from the other type of inversion, that is the surface inversion and upper air inversion, the boundary between the cold air and the warm air mass, unlike the other inversions, is not horizontal in case of. So as you can see in this picture also, the boundary between the cold air and warm air is always sloping, and this is the main uh, characteristic feature for frontal inversion. Now, what are the effects of the temperature inversions? Different kinds of inversions are found to occur within the atmosphere. Some are close to the surface, some are occurring up in the atmosphere. Now, what are their effects? The normal movement and mixing of cold and warm air in the atmosphere creates turbulence, which helps to lift and disperse pollutants. That is in the normal case. Temperature inversions, however, keep cool, dense air near the surface, reducing the vertical movement. And due to the temperature inversion, when the dense cool air occurs close to the surface, the pollutants also stay near the surface. At the surface condition, pollutants becomes concentrate and it affects badly to the organisms living at the earth's surface, and sometimes it becomes hazardous. So all the pollutants, they are concentrating gradually into the or close to the superficial condition. Now, along with breathing, along in the respiration process, these pollutants will go to the lungs of every organisms. So that becomes hazardous if more and more temperature inversions are found to occur. Some of the most significant consequences of temperature inversions are the extreme weather conditions like freezing storms and tornadoes or prolonged smog. So these are the extreme cases found to occur due to the temperature inversion. So thank you.